right, so this is the last section in chapter 2 in calculus, so section 2.3 continuity. This is on page 20 in your notes, and we talked a lot about this back in chapter 3. So we talked about removable discontinuities, infinite discontinuities, jump discontinuities. So we're going to be reviewing that and adding on a little bit. So we talked about this before. Any function y equals f of x whose graph can be sketched in one continuous motion without lifting the pencil is an example of a continuous function. So that was kind of our baby definition. So example 1 is asking us to find the points at which the function below is continuous and the points at which the function is discontinuous. So remember we talked about that continuity test that, at that value the function needed to exist and that you approach the same value from the left and from the right. So when you look at this, maybe first think about where do you have discontinuities? Where do you have holes in the graph? Where do you have maybe asymptotes? Maybe where do you have a jump? Well, let's change this to say discontinuous. Okay, so we can see it's discontinuous here at 1, right? Because as you approach 1 from the left and from the right, you're approaching two different y values. Remember, that's an example of a jump discontinuity. So it's discontinuous at x equals 1. It's discontinuous at x equals 2 because you have this hole in the graph, right? So you approach the same value from the left and the right, but f of 2 is a different value. So it's discontinuous at 1 and 2, and it's continuous on at all values from 0 to 4, but at x equals 1 and x equals 2. So in general, again, when we talk about continuity, what we're talking about is we approach a specific value. So in this case, we're approaching c from the left and from the right. We want to be approaching the same y value. So that was part of our rule before. And the y value that we're approaching needs to be f of c, so the y value at c. So that's our definition right here for a two-sided being continuous from both sides. Okay, so this right here, when it says the limit of f of x as x approaches c, right here, remember what that means is that the limit of f of x as x approaches c from the right equals the limit of f of x as x approaches c from the left, and that both of those values are equal to f of c. So basically the y value at c. So that goes back to our continuity test from chapter 3. Okay, then here, if you're trying to see if something's continuous at an endpoint, so like here at this left endpoint or at this right endpoint, what you're just checking for is that for this one, that as you approach a from the right, that limit exists and that it's equal to f of a. And if you're trying to figure out if this is continuous here at the right end, that the limit as you approach from the left exists and that equals f of b. So that's what this is saying right here. So if a function f is not continuous at a point c, we say that f is discontinuous at c, and that c is a point of discontinuity of f. Okay? And then it says also note that c does not have to be in the domain of f. So like if you had a vertical asymptote, we could still be looking for continuity there. All right, so here, find the points of continuity and the points of discontinuity of the greatest integer function. Okay, so we see that we have all these jumps, and we've talked about before we have all these jump discontinuities. But anywhere else, like in between here, if I picked any of these points and from the left and to the right, I would be approaching the same y value, and that would be equal to the y value there. And all these other values, it's continuous. So it's continuous at every non-integer, and it's discontinuous. We have a jump at every integer. Okay, and because we could say, like, let's say we were checking it at 2. So the limit of f of x as x approaches 2 from the right. So if I'm approaching 2 from the right, my limit would be 2. If I was approaching 2, let's say from the left, my y value would be 1. Because those are not the same, that means it's not continuous. The left and right hand limits are different. Okay, so here we have the three types of discontinuities we talked about before, and then a bonus one. So removable discontinuities. When we talked about these back in Chapter 3, we also referred to them as point discontinuities. So a point discontinuity is when we have a hole in the graph. So basically the limit as you approach from the right and the left is the same. So the limit of f of x as x approaches c from the right and from the left is the same, but those values are not equal to f of c. And when we talked about these before, a point discontinuity also would give us a hole in the graph. And when you would, like, if you could factor anything, it was that the factors would cancel. Let's see, factors cancel. So removable discontinuities are also called point discontinuities, which give you a hole in the graph, and we would have a factor that cancels from the top and the bottom if it was something that could be written as a fraction. A jump discontinuity is like what we see here, which is when the left and right hand limits, those limits there end up being different. So when the left and right hand limits are different, that's a jump discontinuity. And in a lot of cases when we saw these before, these are often piecewise functions. Not always, but they were often piecewise. All right, an infinite discontinuity, sometimes also called essential, was something where you would get a vertical asymptote when you graphed it. And so what that would mean is that the limit, and we talked about this in lesson 2, as you approach c from either the right or the left, is equal to positive or negative infinity. That's how you know you have a vertical asymptote. Okay. And if it was something rational, it would be that the factor does not cancel. Okay. And then the last one that we haven't talked about before, we've sort of seen a little bit when we talked about sine functions, or no, not sine functions, but the other type is called an oscillating discontinuity. So it's that it flips between two different extrema. And to be honest, we're not going to do a ton with this. Okay, so if you look at these 6 graphs, and some of them didn't come out super well because you can't in this one see there's supposed to be a hole here, and they should have arrows on them, so this graphic did not come through very well. So I'm going to kind of add on to this a little bit. So what I want you to do is take a minute, maybe pause the video, and look at each of these and decide what type of discontinuity you have in each case. So the highlighting is the graph that you should be looking at, and you're given, some of them you're given an equation, like this one and that one, you're given equations. But maybe pause the video and think about it on your own. What type of discontinuity you have for each of them. Okay. So this one, this is continuous, right? There are no holes, there are no breaks, there are no asymptotes. This one's continuous. Here we have a hole in the graph. Okay, so that's a removable or a point discontinuity. This one I have a hole in the graph and I have a value here at 2. It's still a removable or a point discontinuity. And we can see, if we kind of went back to that definition, that the limit of our function as x approaches 0 from the right is, so as I approach from the right, is 1, and the limit as I approach from the left is also 1, but f of 0, so at 0, what's the f value? Is 2, okay? So here the limit exists, but because these are not the same, that's why it's discontinuous. Okay, now this one here, my discontinuity is at 0, and so the limit as I approach 0 from the right is 1, and the limit as I approach 0 from the left is 0. Because those are not equal, that makes that a jump. Okay, so if we go back up to our definition, it was that the left and right hand limits are different. So we see those are different, that's why it's a jump. Okay, when it's a point, these limits are the same, but they're not equal to f of that c value. Okay, here at 0, the limit as I approach 0, again, that's where I have my discontinuity from the right, so as I approach 0 from the right, I'm going up to infinity, right? And as I approach 0 from the left, up to infinity, really, so this is from positive or net as I approach from the left or the right, both infinity. If my limit as I approach a value is infinity, then I know that's an infinite or essential discontinuity. Here is an example of something oscillating that's going back and forth and back and forth. It's undefined at 0 because I put 0 in, I would get a 0 in the denominator. All right, so next, removing a discontinuity. So I want you to take a minute, pause, and I want you to try this activity. So following the steps, try the activity, then unpause it, come back, and see if what you came up with matches. All right, so it says factor the denominator, and then what is the domain of f? Okay, I'm going to go ahead and I'm just going to factor this whole thing and see what I come up with. So you can put this into your calculator to factor if you want. So just the factoring part, what is the domain? Okay, I can put anything in here, but I can't have 0 in the denominator. So basically it's all real numbers not equal to positive or negative 3. Okay, and then it says investigate the graph of f around 3, x equals 3, to see that f has a removable discontinuity at x equals 3. So here's our graph right here. And when I look at it, I don't see any discontinuities, but remember our graph doesn't show holes because it connects pixels. So if I hit Control T and I look at 3, I see that it's undefined. Okay, so that usually means there's a hole in our graph because I don't have a vertical asymptote. So I have a hole in the graph, right? So that means there's a removable discontinuity. And then it says, how should f be defined at x equals 3 to remove the discontinuity? You zoom in the tables as necessary. Okay, well, what I'm going to do instead of that actually is I'm going to use that graph trace trick. So I'm going to go to menu, and then 5 for trace, and 1 for graph trace. And I'm going to see what happens as I get really, really close to 3. So if I put in numbers really close to 3, like let's start with 2.5. Okay, it's 2.866. And if I put in 2. Let's say 7, 3.05. If I put in 2.8, 2.9, what does it seem like it's getting closer to? 2.99. So as I get really close to 3, 3.32, 2.9999, 3.33. Let's put in a few more 9s at the end there. Okay, so it's just saying 3.3, 3.3, 3.3. So it's looking like if I let y equal 3.3 repeating when x equals 3, that I could fill the hole. All right, so now it's saying show that x minus 3 is a factor of the numerator of f and remove all common factors. Now compute the limit as x approaches 3 of the reduced form. So, okay, if I look back up here, we might have noticed before, these factors would cancel. Okay, that told us before it was a removable discontinuity. So if I do that and write my resulting function here, I would have x plus 1 times x plus 2 all over x plus 3. And then now it's saying to find the limit of this as x approaches 3. Well, remember, all we had to do to find the limit as you approached a number that wouldn't give you a 0 in the bottom would be to plug 3 in for x. So this would be what, 4 times 8. So, oh, this is supposed to be a 2. Hello. Okay, so 4 times 5, so that's 20 over 6, which is 10/3, which guess what that reduces to, guys? 3.33. All right, so what we've basically done was we've written an extended function that basically fills in the hole and now it creates a continuous function. So now it's saying show the extended function so that if I have this rule for anything not equal to 3, and then I define at 3 my y value to be 10/3, that would fill the hole. So now we have a continuous extension of the original function that includes the x equals 3 where I had the discontinuity before. All right, so now this next one, find and identify the points of discontinuity. So whenever we want to have a fraction, we're thinking, okay, what makes the bottom equal 0? Okay, so when I look at this, what would make the bottom 0? X equals 1. And so then I want to figure out, okay, well, what type of discontinuity is it? The easiest way to do that would be to graph it. And the graph, you can put it in your calculator. I happen to know the shape of this one. It looks like this. It's called the inverse square curve. So if I looked at the graph, I would see at 1 that I have vertical asymptotes, right? So the limit as I approach 1 from the left and the right is infinity. So this is a vertical asymptote. So this is an infinite discontinuity. All right, and I think we talked about this next part before, continuous functions. So you might have a function that's discontinuous, so like let's say this one, but if I looked at just a section of it, so if I just looked at that little part there, that little part there is continuous. So we can say that a function is continuous on an interval if and only if it is continuous at every point in the interval. So that would be like if I just said, okay, this is continuous from -infinity to 1. Okay, then the next part, a continuous function is one that is continuous at every point in its domain. A continuous function need not be continuous on every interval. Okay, so sometimes people get confused about this. So up until now, we've been talking about continuity at a specific value. Is this continuous at x equals 1? No, and then y. This is talking about a continuous function, and it's saying it's continuous at every point of its domain. So if I looked at this function here and I said, okay, well, what's the domain? The domain of this is all real numbers not equal to 0. So now if I said, is this continuous on every value of its domain? I would say, yeah, it actually is, because if I'm not including the 0, it's continuous here and it is continuous here. So y equals 1 over x is actually continuous at every point in its domain. It's kind of like a trick. So we can say this is a continuous function because 0 is not included in the domain. Now if I said, is this continuous at 0, you'd say, nope, it's not. It's an infinite discontinuity. All right, so next, we have properties of continuous functions, just like we have properties of limits. So if I had a function that could be broken down into two parts, if each of those parts are continuous, then the sum of the parts, the difference, the products, the multiples, the quotients, provided it doesn't equal 0, those are all also continuous. Another operation that we talked about before, back in maybe it was chapter 3, I think again, was composition of functions. And so composition of continuous functions. So that says if f is continuous at c and g is continuous at f of c, then the composition of g of f is continuous at c. Okay, so the way we can think about this is if I were to, let's say, take this function here and break it down into two different functions that I could then create the compositive. So let's say, I'm going to first rename this. I'm going to rename this f of x. Okay, and if I let kind of the inside, or the inside of this be one function, so let's say I let the inside of my function, I'm going to say g of x equal sine, or x times the sine of x over x squared plus 2. And then I kind of let the outer, the rule surrounding that, be another function. So let's say h of x is just the absolute value. Then what I can do is I can look at these both individually and decide, okay, if this is continuous and if this is continuous, then the composition h of g of x, which is equal to f of x, is also continuous. So first let's just make sure that you agree that h of g of x is equal to f of x. So h of g of x would mean that I take g of x and I plug that in here for x. So h of g of x would be the absolute value of that whole thing. Okay, so we agree that that's f of x. And so the idea is that I can break it into two different things. So mathematicians, if they didn't know like what that looked like, they might know what this looks like, they might know what this looks like, so then they could decide that the composition is continuous. So if we look at this, and you're probably looking at this saying, how the heck am I supposed to know if that's continuous? Think about, is there anything that would make your bottom 0? Because that's what gives us discontinuities. And because you're squaring and then adding, there's nothing that would make your bottom 0. So since g of x is continuous, and that's just an absolute value graph. We know what that looks like. That's continuous. So g of x and h of x are continuous for all values in their domains. It's important to have this part in here about all values in their domains. Then h of g of x, which equals f of x, is also continuous. Okay, so sometimes people get confused about like, well, how am I supposed to decide what's the g of x and what's the h of x? So let me make up another one. Let's say I had this, f of x equals the square root of x minus 3. And I had to decide, okay, what's my g of x, what's my f of x? So think about when you read that, you start by saying the square root of x minus 3. What you're taking the square root of is like your g of x, and the operation on the outside is your h of x. And really, it wouldn't matter, like if you had those interchanged. You just have to be careful so that when you write out this kind of line here, that this is equal to f of x. So as you're reading it, you're saying the square root of, that outside operation is one of your functions, and what you're taking the operation of, your argument, is the other function. Okay, because think about it. If I wrote h of g of x, that would mean I would take this and plunk that in place of the x, which is equivalent to f of x. And then you would think, okay, well, is this continuous? Well, that's just a line. Is this continuous? Well, that's just a square root. And because both of them are continuous, then h of g of x is also continuous. All right, and then last one thing, intermediate value theorem for continuous functions. So a function is said to have the intermediate value property if it never takes on two values without taking on all the values in between. And so if I look at this function, and it says a function f y equals f of x that is continuous on a closed interval from a to b, so here's a, here's b, takes on every value between f of a and f of b. So here's the y value for a, here's the y value for b. If something is continuous, it means it's hitting every possible y value in between. There are no breaks. Okay, so this theorem is the reason why the graph of a function continuous on an interval cannot have any breaks. The graph will be connected, a single unbroken curve. It will not have any jumps or separate branches. Okay, so that's it for 2-3, and then the assignment for that follows starting on page 25.